This presentation is delivered by the Stanford Center for Professional Development.
So today we'll continue with the conjugate gradient stuff. So last time, let me just review sort of where we were. It was actually yesterday, but logically, in fact, but we can pretend it's 5 days or whatever it would be. So we're looking at solving symmetric positive definite systems of equations, and this would come up in Newton's method. It comes up in interior point methods, least squares, all these sorts of things. And last time we talked about, the CG method. The basic idea is it's a method which solves AX equals B, where A is positive definite, but it does so in a different way. The way you've seen before are factor solve methods. And in fact, in those methods, what you need is you actually need the matrix. So you pass a pointer to an array of numbers, roughly, and then you work on that. What's extremely interesting about the CG method is actually the way A is described is completely different. You do not give a set of numbers. In fact, in most of the interesting applications of CG, you will never form or store the matrix A, ever. Because in fact, in most cases, it's huge. It's some vast thing. That's kind of the point. Instead, what you need is simply a method for calculating A times a vector. So what you really are going to pass into a CG method is a pointer to a function that evaluates this thing. How it evaluates it is its business. It's none of your business. That's sort of that's the idea. Okay. Well, last time we started looking at a little bit about this. We looked at two different measures of the error. So one measure is this number tau, and it's the amount of decrease f is that quadratic function you're minimizing. You've achieved divided by this is the amount of the decrease, the suboptimality in decrease, divided by the original suboptimality of decrease. That's probably what you're interested in. But another one, which is probably in many applications what's actually easier to get a handle on and all that sort of stuff, is the residual. And the residual is nothing but b minus ax. It's basically how far are you from solving ax minus b. Now, the CG method, actually and many others, actually work with the idea of a Krylov subspace. And this is just to sort of rapidly review what we did last time. The Krylov sequence of a set of vectors is defined this way. It's actually, you take this Krylov subspace, and that's the span of b, ab, up to some ak minus 1b. And that essentially means it's all vectors that can be written this way. It's b times a polynomial of a, and that polynomial is of degree k minus 1. That's a subspace of dimension, could be k, but it actually can be less. Actually, if it's less than k, then it means in fact, it means you've solved the problem. Okay, so xk is the minimum of this. This is the function you're minimizing, this quadratic function on the Krylov subspace. It's the minimizer of that. And the CG algorithm and several others, right, generate the Krylov sequence. That's actually the important part. Now, in the Krylov, along the Krylov sequence, obviously, this quadratic function that you're minimizing decreases. That's obvious because, in fact, you're minimizing over a bigger and bigger subspace at each step, and that can't get worse. Now, the residual can actually increase. That's not monotone. Now, it turns out if you run n steps, you get x star. That follows from Cayley-Hamilton theorem. And the kth iterate of the Krylov sequence is actually a polynomial of degree k minus 1 or less multiplied by b. Now, the interesting part and the reason why these methods actually work really well, although, by the way, there's plenty of cases where you're going to do this for such small number of steps that this is actually not that relevant. There's a two-term recurrence, and the two-term recurrence is this. You're going to, you can compute the next point in the Krylov sequence actually as a linear combination of not just the previous one, but the previous one and the one before that. and then there's some coefficients here. And we'll see what the coefficients are later. Actually, they're not that relevant. What matters is that they exist and are easily calculated. Okay, so we've seen this. And what I want to do now is look at the, to understand how CG method works or how well it does. It's extremely important to get a good intuitive feel for how it works. When is it going to work well? By the way, notice that you would never even say anything like that when you talk about, like, direct methods. You wouldn't say it's good to talk about, let's say, well, here's a 1,000 by 1,000 matrix. Oh yeah, here's when it's going to work well. It always works well. You have positive definite matrix, you take a Cholesky factorization. It doesn't depend on the data. I mean, to first and to zeroth and first order does not depend on the data. Okay, with these though, you need to know when is it going to work well, because that's actually the key to all of these things. So the way to do this is essentially to diagonalize the system. Now when you diagonalize, it's kind of stupid, because if A is diagonal and I ask you how do you solve AX equals B, that's easy. That's just A inverse B. A is diagonal. So the solution, if I diagonalize, is actually just this. It's just the transformed B divided by the ith entry in the transformed A, which is diagonal. It's this lambda thing here. So that's very simple. But this is gonna give us an idea for when this works well. The optimal value is just this. It's nothing but this thing. That's that A inverse B star A inverse B. That's this thing here. Okay? Okay. Now the Krylov sequence in terms of Y is the same, except now we can actually look very carefully at this thing, because the polynomial of a matrix is really, really simple. The matrix is diagonal. So a polynomial of it is simply the polynomial. It's a diagonal matrix, and each entry is a polynomial of that entry in the diagonal, which are the eigenvalues of A. So you get very simple expressions all in terms of the eigenvalues now. So it says that pk is one way to say it is the polynomial of degree less than k that minimizes this sum. And notice it's got some positive weights here, non-negative weights here. And then over here you can kind of see what's going on. If you look carefully at this, you really want P, well, we'll say what P should look like in a minute. P should look like 1 over lambda or something like that to make this work well. Okay. So another way to write it, let's just keep going down here, is we'll look at the second expression. The second expression says that this error is the minimum over that. These are the positive weights, and then here you can see it's lambda I times lambda I P of lambda I minus 1. And in fact, what that says is if you can make P of lambda look like 1 over lambda on the eigenvalues of A, in fact, if you could have P of lambda I equals 1 over lambda I, it's done. This is 0, and then that says that in fact this would have to equal F star. Okay, so that's the idea. And in fact, we saw already in the Cayley-Hamilton theorem that there's an nth degree polynomial, which in fact we saw exactly what Pn is. It has to do with a characteristic polynomial. It's a polynomial that in all cases satisfies P of lambda I equals 1 over lambda I, and that's why this converges in 10 steps, or in n steps. Now what's interesting here is this is going to give us sort of the intuition about when this works well. There are lots of other ways to say it. I mean, one is to say, well, look, a polynomial, something that looks like that is a general polynomial of degree k with the value that if you plug in 0, this goes away, you get 1. I mean, I switched the sign on it. So that's another way to say it, is this way. There are lots of these. I won't go into too many of the details, but the important part are the conclusions. So here are the conclusions. If you can find a polynomial of degree k that starts at 1, that's small on the spectrum of A, then the kth, then actually no matter what the right-hand side B is, your f of xk minus f star is going to be small. And in particular, this says that if the eigenvalues are clustered into groups, let's say k groups, then yk is going to be a really good approximate solution, because if I have k clusters of eigenvalues, I can take a kth order polynomial and put it right through, say, the center of those clusters or near the center of those clusters, and then that polynomial will be really small on each of those clusters, and we'll get a very good fit here. Now, there's another way to do well, and that's to have yi star small for just a handful of things. So this says, if your solution is approximate linear combination of k eigenvectors, then yk is a good approximate solution. So that's another way to say it. Notice that this statement is independent of the right-hand side and depends only on the matrix A. This one now depends on the right-hand side, but doesn't depend on the clustering. It basically says if you're a linear combination of k eigenvectors, then this must be a good solution. So, okay. Now you can do things like this. This allows you, these are classical bounds. Classical bounds would be things like this. You would, suppose the only thing I told you about A was that its condition number is kappa. So I give you, let's say I can scale A. So I give you lambda min and lambda max. And if I put a Chebyshev polynomial on there, that's a polynomial that's small uniformly across it on that interval, you end up with a conclusion that says this. It says that this convergence measure, this thing goes down like that. And this is actually, this allows you to, by the way, a simple gradient method would have a kappa here and a kappa here. So if you just use a gradient method to minimize that function f, you'd get kappa here and kappa here. And so you're supposed to say, wow, that's much better because you get square root here or something. So that's the idea. It turns out this is interesting and that's fine, but it turns out actually that where you want to use CG is where, in fact, I mean, this is like many other things. It's an upper bound, and in fact, you usually get convergence that's sort of much, much faster. Not to high accuracy, but so let's do an example here. So these show you, this is the function q. They all start at 1 here. It's a 7 by 7 matrix. Now, I think it goes without saying that CG is not the method of choice for solving a 7 by 7 positive definite system. That's something, I guess the time to actually solve a 7 by 7 positive definite system is down in the, it's definitely sub-microsecond, obviously. So this is not the right way. Nevertheless, this is sort of the, we'll just look at an example. So here are the eigenvalues of A. I don't know, there's one here, I guess it's around 2. A couple down here, another cluster here, and an outlier out there. After one step of CG, the optimal Q is this thing. By the way, it goes without saying you don't ever produce these. I mean, if you want to keep track of these polynomials, that's fine, but you don't need to. So this shows you that one, and you can see it. It's kind of doing its best. It's not so small here, nor is it small here, and it's pretty big there. The quadratic is this green one, and you can see it gets small near this cluster, and it kind of splits this cluster and goes near it, so that you get things like this. The cube term, I think that might be the purple one here, is the cubic term. And you can see now cubic is nice because it's sort of, you can see 3 clusters, and it does just what you think. It goes down, goes right through this thing. It's very small here. Small here, small here. Over here it's very, quite small, still small, and then kind of goes down there. It's small here. So actually you could expect that after 3 steps of this method, you're going to get a very good solution. The quartic, I think, is the red, maybe. I guess maybe that's the red. I'm not sure. I guess that's the quartic or something. And the quartic one, you can see, goes through, is now actually picking off bits and pieces. It's actually doing things like hitting both sides of this, so it's small on all 3 here, it's small here, and now it's just nailing that one. And then the 7th one is this one, and that's actually an interpolating polynomial, so it's 0 on all of them, and that means that at step 7 you get the exact answer. Okay, so, I mean, actually I'm anthropomorphizing this, obviously. Well, all that's actually done is the Krylov sequence is computed. But this gives you a rough idea of how this works. Okay. Actually, you'll know shortly why it is that you need to know how well CG works, because it's going to be your job to change coordinates to make CG work. We'll see that in a minute. Okay, so here's the convergence, and sure enough, you know, you start with, that's the full decrease, and you can see that sort of after 5 steps you've done very well, and I guess after 4 you've done extremely well, and so on. So that's the picture. Okay, here's the residual, which in fact does go down monotonically. Didn't have to, but it did in this case. Now we'll look at it. I mean, that's a fake example. Let's look at a real one. Here's an example. It's just a resistor network with 100,000 nodes. We just made it's a random graph, so each node is connected to an average of 10 other nodes. So, you know, some big complicated resistor network. So I get 1,000,000 non-zeros in the matrix G. And I pick one node and I make that the ground. Okay? Then I'm going to do the following. I'm going to inject at each of the 1,000,000 nodes a uniform current. A current that's chosen randomly uniform on 0, 1, and the resistor values will be uniform on 0, 1. Okay, so that's the problem. It doesn't matter, but in this case, if you wanted to use a sparse Cholesky factorization, actually before you even do it, you'll know what happens because you can actually do the symbolic factorization on G and actually calculate the number of fill-ins. Okay, so in this case, it required. There was too much fill-in, and I don't know. I don't know how big it would be, but maybe I don't know, 50 million or 100 million or something like that, non-zeros, starting from 1 million. Right, so, oh, I should mention this: if the number of non-zeros goes up by a factor of 2, you are to consider yourself lucky in a sparse matrix thing, right? And that means you must go and make an offering to the god that controls the heuristics of sparse orderings of orderings in sparse matrix methods. 10, you know, that's okay. You're supposed to be happy, or that's typical. You start getting to fill-in factors like 100 and stuff like that, and that's because you didn't go make an offering the last time sparse matrices went your way. So all right. So in this case, this problem you can't solve with a sparse Cholesky factorization. And I actually shouldn't say that. I should say using the approximate minimum degree ordering method produces a Cholesky factor with too much fill-in. Now, of course, on a big machine, I actually could have done it and would have gotten the exact answer, but it would have been really long and taken a lot of time. It might be that there's another heuristic ordering method that would work perfectly well here. I doubt it, but anyway, there's lots of them. Okay. So instead we'll use CG here. Now in this case I do form the matrix G explicitly, and all I have to do at each step is I have to multiply by G. But that's just a sparse matrix vector multiply is 1,000,000 non-zeros. So I'm doing like 1,000,000 flops, a million flops per matrix vector multiply. And that's the dominant effort of a CG iteration. So I don't know, how much time does that take? A second. Man, I gotta work on you guys. This is not cool. What?
Less than a millisecond?
What?
Less than a millisecond?
Thank you. Less than a millisecond. So around a millisecond, let's just say a millisecond. And let's just get the order of magnitude right. Millisecond. Okay, so matrix vector multiply is a millisecond here, roughly. Is that right? Thousandth of, yeah, sounds about right, right? Yeah, sure. Weird. Isn't that strange? Man, these computers are fast these days. Okay, that shocks me. Anyway, all right, so it's a millisecond, matrix vector multiply. Yeah, it might be a few milliseconds because of all sorts of, you know, issues with accessing memory and stuff like that. But if it's set up right and you're lucky, it's on that order of magnitude. Okay, so here's how CG runs, and this is the residual here. So, and you can see that, well, for 10 steps, the residual actually goes up by a factor of 100, generally considered not good. And then it goes back down again. But the wild thing is, the theory tells us the following. The theory says that if you run it what was 100,000? Yeah, the theory says if you run it 100,000, the millisecond doesn't sound right to me, but I'll have to think about that. I think that's, do I have to do that for each one? Or so? Anyway, maybe it is right. Oh, doesn't matter. The theory tells you that if k here runs out to 10 to the 5, we'll get the solution exactly. But the wild part is if you're not picky about super high accuracy, you actually have a perfectly good solution in 50 steps. Okay. Each step was a matrix vector multiply. And if our estimate of a millisecond is right, it means you just solved a very large, diffusion equation, Poisson equation, whatever you want to call it. You just solved it in a quarter second. I mean, if we're right, or something like the 1/10 of a second. Everybody see what's going on here? By the way, absolutely nothing in theory guaranteed that this would happen. Absolutely nothing. Okay, it just did, and this is very common. So, and this is kind of the cool part about CG is that in a shockingly small number of steps, what emerges is something that looks kind of like the solution. In this case, it doesn't look like the solution. It's actually like quite good. Okay, so that's the idea. So if you wanted to know at what point have you learned something new, you just did. You cannot if you just type this thing, G\I or whatever, and let us parse, even if you have a big computer, it's going to take a long time and a lot of RAM. And then this will just get a pretty good answer in 50 steps and just be way, way shorter. Okay? Okay. So here is the CG algorithm. There are many variations on it. People seem to focus more on the algorithm itself than actually on what the algorithm produces. In my opinion, it's much more important what the algorithm produces, which is the Krylov sequence. And there are other methods to produce the Krylov sequence, and they have different round-off properties and things like that. Let me show you what those are. So here's one, and this is, instead of just sort of making up my own, I just followed exactly one from a very good book on this subject by Kelly. So just to make it, not to invent new notation or anything, it's this. And the only important part you need to know here is something like this. You maintain the square of the residual at each step. If the residual is small enough, you quit. So this quitting criterion, epsilon, is on the ratio, it's what we call eta. It's on the ratio of the current residual to the norm of B. That's this thing. And what you do now is something like this. Your search direction is going to be something like P, and it's a combination of both the current residual and the previous search direction. Then all of the effort in here, well, not necessarily, but in most cases, is right there. This one thing right here. This is where you call the mult by A method is called right here. Everything else, if you look here, is actually sort of an O of n or a blast level 1 or however you want to call it, call. So for example, here you update a vector, that's O of n, that's O of n. You have to calculate an inner product. Actually, if you want to parallelize this, that's the one that is really irritating. Everything else here can be done is completely distributed. So the main effort here is this call to A. These other things, I guess this also has to be collected together. So that's another one that would not be distributed easily. But that's the algorithm. By the way, these calculations can be rearranged like 50 different ways. And so you get different versions of it. In exact arithmetic, all of those ways will compute exactly the same sequence xk. With round-off errors in there, they can be different, and you'll find people talking about one versus the other and this, that, and the other thing. And you'll find all sorts of different flavors and things like that. And people telling you one way is better than another and all that. So, yeah?
Is there any way to know, like, if it will be faster than theoretical convergence?
No. I think the theory just gives you like rough guidelines. It basically says if the eigenvalues are clustered, if they're for example, if they're tight, if the condition number of the matrix is small, that condition number bound will tell you it's going to nail it in 50 steps. Okay? If they're spread out but have clusters or something like that, it's going to nail it. That kind of thing. So in general, you don't know. Kind of the worst things you can have are ones whose spectrum is sort of uniformly spread all over the place. Right? That's the kind of the worst thing. Now, it also depends on the right-hand side. So if the right-hand side, the B, actually, if that one, the worst thing that can happen is B can be sort of a uniform mixture of all the eigenvectors. I mean, that would be kind of the worst thing to happen or something like that. Okay. So let's talk about, so as I said at the beginning, this is mostly interesting. I mean, there's a fundamental difference between this and a direct method. In a direct method, you give the matrix A, you give the coefficients to the algorithm, literally. You pass an array or some data structure and you get the entries. In CG, you do not need that. All you need is a method that multiplies by your matrix A. There's nothing else you need. Okay. That actually, in interesting cases, that can be some like specialized hardware. It could actually carry out an actual experiment. I mean, it could solve a whole PDE. It could do insane things, right? Do a full-up simulation of something, run Monte Carlo. It could be all sorts of weird stuff. But it doesn't have to be a matrix is the point. So here are some examples. When can you do an efficient matrix vector multiply? These are kind of obvious. If A is sparse, for example, if it's sparse plus low rank, now you better know the factorization here. And if you want some numbers here, you should just think of A as like 1,000,000 by 1,000,000. That's just kind of, because if A is, I don't know, 10,000 or something, this is kind of not worth it or something. Yeah, so you should just, your mental image should be the A is 1,000,000 by 1,000,000 or 10,000,000 by 10,000,000. That's a good number, 100,000,000 by 100,000,000. These are the numbers you want to think about when you think of CG and how these things work. If you have products of easy to multiply matrices, that works. Fast transforms come up. So FFT, wavelet, DCT, these types of things. Things like fast Gauss transform, that actually is with A looks like this, and you do this via multipole methods. This is actually an extremely interesting one. Here's a matrix that is extremely, that is dense, well, half dense, and that's this. The inverse of a lower triangular matrix. In fact, even the inverse of a sparse lower triangular matrix. That's a great example. So I give you a sparse lower triangular matrix. By the way, the inverse of that is generally completely dense. So what that, yeah, and I couldn't even store, let's make it 1,000,000 by 1,000,000. In fact, let's make it 1,000,000 by 1,000,000 banded. The Cholesky factorization of 1,000,000 by 1,000,000 banded, of course I could solve that directly, but anyway. 1,000,000 by 1,000,000 banded or something like that is actually also going to be banded. It's going to be lower. It's going to have, it's small. It's easy to do. The inverse is going to be a full lower triangular matrix. You can't even store it, and it would be completely foolish to actually calculate the inverse matrix and then multiply each time. But if I give you a vector and I ask you to multiply by the inverse, it means you have to solve a lower triangular set of equations, and that you can do by back substitution. If it's, I'm assuming, I'm taking the case where it's sparse. Okay, so these are just examples. It's very good to think of examples like this. Okay, now a couple things you can do. You can also shift things around. So if you have a guess x hat of the solution x star, then in fact what you can do is actually, well, this is the residual with your guess. If you solve AZ equals this residual, then your solution is actually going to be just, if you solve this, you get the optimal Z and you add it to x hat, and that's your solution. What happens now is that xk now looks like this. It's actually x hat plus this, and it's the argument of this quadratic over the shifted Krylov subspace. So you shift by this x hat. And there's nothing you have to do to make this happen. All you need to do is initialize not with 0 in the first step, but with x hat, and everything will work. Now, this is also very important, because this is good for warm start. So what this means is, if you need to solve, let's say, a giant circuit equation, giant resistor equation, if that's part of integrating, integrating a circuit, integrating a differential equation for a circuit, you will step forward a couple of picoseconds or whatever, and you'll solve a similar system. You can use the last thing you just calculated as your guess, and this can often give you like stunningly good results. So actually, we'll see an application of that in optimization soon. So, okay, but now we come to the real way it's used. And I should say this. I should say that if you, in most cases, if you simply run CG on a problem, it won't work. The theory says it will work, but that's not relevant for several reasons. It's not relevant, number one, because you have no intention of doing a million, if you have a 1,000,000 dimensional system, you have no intention of running 1,000,000 steps because you don't have that time. You don't have that much time. That's the first thing. So to say that it works in practice means that it works in some very modest number of steps. A lot of people, I remember hearing, here's something you hear on the streets, that you're doing okay when CG, when you're pulling, you're doing right pretty well when you're doing square root n steps. Theory says you have to do n, but the word on the streets is square root n should do the trick for you. And if you think carefully about what that means, it's just a rule of thumb. It says if you have 1,000,000 variables, in 1,000 steps you should have a pretty good solution. Okay? These are just, I'm just saying these. It could be slow, you know, but you shouldn't be shocked if it's on the order of square root n. That should be the target. So 100 million, 10,000, that kind of thing. Okay? These are the numbers. Okay. And the other reason it's not that relevant is the following. The theory is that errors when you're doing conjugate gradients, round off errors, they actually add, it's unstable, and the thing diverges. Actually very quickly. So by itself, CG generally often will just fail. If you just have some problem and you run it, it's just going to fail. Okay. So the trick in CG is actually changing coordinates and then running CG on the system in the changed coordinates. That's the trick. That's called preconditioning. Now you know why it is that you needed to know when CG works. Because the key idea now is to change coordinates to make the spectrum of A, for example, to make the spectrum of A clustered or something like that, or live in a small interval. So that's the key. Okay. So here's the basic idea. You're going to change coordinates. You're going to use y. Is the coordinates of x in some t expansion. And what's going to happen is you're going to solve this equation here, and then in the end, set x star as t inverse y. Then sometimes people call t the preconditioner, but then sometimes they call tt transpose the preconditioner. And you get all combinations of preconditioner meaning t, t transpose, m, t inverse, and t minus transpose. So there may be some other possibilities, like m inverse. But so the point is that anytime anybody says preconditioner, you have to look very carefully and figure out exactly what they mean. Okay, so that's the preconditioner. And basically what happens is if you just take CG, it's actually not that bad. So you have to multiply by t and t transpose at each step. The other option is to multiply simply by m once. And you don't really need this final solve, in fact. So this is called PCG. And by the way, this is exactly where this is why in these iterative methods you have room for personal expression. Right? So if you're solving dense equations, there is no room for personal expression. If you do anything other than get BLAS and run Atlas to tune it to your cache sizes and things like that, and then write good code, then then it's just not right. There is no reason under any circumstance to do anything else. Yeah. You go to sparse matrices. Actually, in sparse matrices, is there room for personal expression if you're doing sparse matrix methods? Yeah. And what is it? Ordering. Ordering. Yeah. So there is some room for personal expression in sparse matrices, and as to selection of ordering. And that's cool. Actually, you can say, oh, I know my problem. I know a better ordering than approximate minimum degree is finding, or something like that. Or there's exotic ordering methods. You can go look at Netis. There's a whole giant repository at Minnesota that's got all sorts of partitioning methods, and some of those are rumored to work really well. Okay, but we move up to scale one step higher to iterative methods. Now, boy, is there room for personal expression. And it is mostly expressed through the preconditioner. So, in fact, when you get into these things, you'll find everything is about finding a good preconditioner for your problem. And then you can go nuts, and you can have simple preconditioners and complex ones and unbelievably complex ones and things like that. So that's There's a lot to do. Okay. So the choice of preconditioner is this. Here's what you want. You want the following. You want a matrix T for which T transpose AT, or a matrix M, let's say M. I want a matrix M for which the eigenvalues of MA are clustered, for example. Here's one choice. How about this, the inverse? That'll do it because now the eigenvalues of MA are all 1. CG takes one step because the eigenvalues are all 1. It's kind of stupid, though, because you actually then have to like sort of invert the matrix or something like that. So that doesn't make any sense. So here's what you really want. What you really want is a matrix M which somehow approximately is some kind of approximate. We'll see approximate can be very crude. An approximate inverse of the matrix, and yet is fast to multiply. That's what you want. Okay? So that's the essence of it. And so this is the idea. And this M can be quite. You'll see it. Approximate is like very generous here. I mean, it's you can be way off. Here's some examples. The most famous one, and often very effective, is diagonal preconditioning. It's kind of stupid, but actually you should try that always and immediately first, because it often just works. So you would not call the diagonal of the diagonal of the inverse of the matrix or whatever. You would not call that an excellent approximation of the inverse. But you have to admit it's cheap to multiply and all that kind of stuff. So, and it works quite well. Amazing. Here's another huge family is actually really cool, and it's called incomplete or approximate Cholesky factorization. And so here's how that works. Now, what I'm going to do is I'm going to compute a Cholesky factorization, not of A, but of some A hat. And the way you might do it is something, it's weird. It might work like this. You might run a Cholesky factorization. In fact, there's a whole field on this called incomplete, it's also called ILU, incomplete LU factorization. These are preconditioners based on this. And the way it would work is this. You take the matrix and you start doing a Cholesky factorization on it, but you might decide if an entry is too small when you do Cholesky factorization, you say, screw it. Just forget it. I'm just going to ignore it. Or if you're doing something and you're going to add in, you fill in various places, which is the death of direct methods, you just say, forget it. I'll just ignore it. So you end up calculating a sparse, well, it's a sparse Cholesky factor of something, but it's definitely not the original matrix, right? So these methods also can work really well, these things. And here would be an example. You could do the central K-wide band. That's a version of this. It's a version of this, too, where you just basically say, any fill-in of L below some band, I refuse to even, I won't even go there. So let's see. These are some obvious, anyway, these are sort of the obvious things. These can work really well. And a good example would be something like this. If you have a problem where there's a natural, where something is ordered, for example, in space or in time, like in signal processing or control, you have time. Then what happens is, things are connected locally. States, transitions, signals, and things like that. And that leads to this banded system. Now, banded systems you can solve super fast. We all know that. But supposing you had a dynamic system or signal processing problem, but a few things were kind of, you had a main bandwidth of like 10 or 20, and then a light sprinkling of little things all over the place, everywhere else. So for some weird reason in your problem, the state here is related to the state. It's just, I don't know, I'm just making this up. But the point is you can easily make up an example like that. Everybody see what I'm saying? So it's kind of banded, plus a little light sprinkling of non-zero entries other places, okay? So this would work unbelievably well. You simply do a banded, you simply ignore all the crap off some band. You do a Cholesky factorization on that. That's your preconditioner. And the only thing you're working the error to fix is all that little light sprinkling of entries that were outside that band. So okay. That's the idea. By the way, a lot of this stuff that I'm talking about, I mean, these are whole fields. I mean, this is the basis of all scientific computing, PDEs, all. So there's tons and tons of people who know all of this stuff backwards and forwards. A lot of this stuff, though, hasn't diffused to other groups for some reason. So these are actually just really good things to know about. Okay. So here's that same example with 100,000 nodes and a million resistor circuit. And here it's just with diagonal preconditioning. I mean, it's kind of silly because it was already working unbelievably well, but you can see this is what diagonal preconditioning does. Diagonal preconditioning actually is mostly useful, not for this kind of speed up, but for when this residual goes like this. It goes like that, and then it would go like this. Okay? Theory says it doesn't do that. That's all from round-off error. So that's how they... And in fact, here's a very common CG stopping criterion used on the streets. It's this. You run CG until the answer starts getting worse. And then you stop. And you just say, well, that's it. Sorry. Here's what it is. So, and I know that that's done, and I know people who do that in image processing and computational astronomy and all sorts of things. Like they run CG until that usually only gets you a couple hundred steps, and then basically you can keep running CG, but things are getting worse because the numerical errors, you've lost orthogonality, and all sorts of things happen. Okay. So here's a summary of CG. Actually, the summary is all that matters. So here it is. In theory, and that means with exact arithmetic, it's not particularly relevant. It converges to a solution in n steps, period. That's not interesting or relevant because n, you should think of, is on the order of 1 million, roughly. And the whole point is you have no intention of doing 1 million steps. Your goal is to do it in 1,000 steps, couple hundred, whatever. So that's kind of your goal. Actually, if you're really lucky, 10, 20, 30. These are the numbers you really want. Okay. Now the bad news is that if you is that actually numerical round-off errors actually makes this thing work much worse than you would predict. Now the good news, though, is that with luck, that means a good spectrum of A. You can get good approximate solution in much less than n steps, right? So now. The other main difference with a CG type method or something like that is this, and this is very important. You never form or need the matrix A. Anyway, you can't store a million by million dense matrix anyway. Well, I mean, maybe you could, but the point is you don't want to. So the point is you don't need the matrix. You don't need the coefficients the way it works for direct methods, where you pass in a data structure that's got all the coefficients in it. Okay. Here, you don't need it. What you need only a method to do matrix multiplication. It means you have to rethink in your head everything you knew about linear algebra. And you have to rethink to this model where what you really have is a matrix vector multiply oracle. And that's it. What the oracle does, how it's implemented, is none of your business. You can call it, you can give a vector, and it will come back with AZ. By the way, you could, this would be very bad, but you could actually get the coefficients in A from an oracle. How would you do that, actually?
Multiplying by
EI. Yeah, exactly. So you call the oracle with E1, and what comes back is the first column of A. Then you do it for E2, second column. And actually, after EN, you've got all of A. So then you could pack it in there and then call LA pack, whatever. But that's that's not the point here. Okay. And very important to fix in your mind how this is different from factor solve methods. Okay, it's less reliable. It's data dependent. So, for example, that circuit I showed you, that was with a random topology. I might take another circuit that's got like a pinch point or something in it. 10,000 iterations, nothing happens. Or it's even worse. So it diverges. These are data dependent. Okay, and this is not the case, roughly speaking, for direct methods. They're data dependent. But there is, you can think of this the bad way or the good way. The bad way is this: these methods don't work in general unless you change coordinates with a clever preconditioner. That's the bad way. The good way is to say is that CG methods have lots. I mean, the employment prospects are very positive because you don't just you don't just call a CG method. You need somebody to sit there, figure out the problem, try a bunch of preconditioners, and tune things, and find out what works. So that's you can think of that the good way. There's room for considerable personal expression in CG methods. On the other hand, you can hardly complain. This is really your only method for solving a problem with a million, 10 million, 100 million variables. So if you made the mistake of going into a field where that's needed, then that's your problem.
So when you have A only operator form,
Mm-hmm.
it seems like it'd be hard to get some of the preconditioners you mentioned before. So
Right.
do you just use easier ones?
Yeah, so that's, okay, yeah. So if A is an operator form, usually you know the operator. I mean, typically you know the operator. So it's not this thing where you don't even know what the oracle does. I mean, the theory says you could do that. No, to get, although that, well, let's see, no. It says, so for that, you have to sneak around the oracle. Yeah, it's a good point. You know, you have your, it's not a pure oracle protocol. Just to get the diagonal, you'd sort of sneak, or you'd send a messenger around in back of the protocol and say, would you mind telling me what your diagonal is? And normally, a reasonable oracle will be willing to tell you the diagonal. So, but that's a very good point. If you have to find your diagonal by calls to the oracle, you're screwed. Yeah. Okay. That's. Any other questions about this? Because we'll go on to the next the topic, which is actually just it's kind of obvious. It's just applying this to optimization. Okay. So these are called truncated Newton methods. Actually, there's a lot of other names for it. We'll get to those in a bit. They're called approximate Newton method, truncated, and you can do this all the way up to interior point methods. So let's see how this works. So here's Newton's method. In Newton's method, you want to minimize a smooth convex function, second derivatives. And so what you do is you want to calculate the Newton step by solving this Newton system here. It's symmetric positive definite. That's symmetric positive definite. And you might do that using a Cholesky factorization. This would be the standard method, you know, for problems that are either dense with up to a couple thousand variables, or problems that go up to 10,000 or even 100,000, something like that, but where the sparsity is such that the Cholesky factorization can be carried out. So that's what you do here. And then you do a backtracking line search on the function value. It could be on the function value or the norm, either way. And you'd stop basically based on the Newton decrement, that's this thing, or the norm of the gradient. So that would be your typical stopping criterion. Okay. Oops. Okay, so an approximate or inexact Newton method goes like this. Instead of solving that Newton system exactly, we're going to solve it approximately. And the argument there is something like this. You don't really have to get the Newton direction exactly. That's kind of silly. In fact, for sort of convergence, you only need a descent direction. Of course, the whole point, the advantage of Newton's method is these, especially for these smooth convex functions, is that it works so unbelievably well, and you get your final quadratic convergence and things like that. So what you really want is to trade off two things. What you want to do is you want to do a fast and sort of crappy job of approximately computing the Newton steps. You want to get a fast delta x. But if it's too crappy a job, then the algorithm is actually going to make slow progress. By the way, as to whether or not it's going to make progress at all, it'll always make progress because you will see that almost any method for approximately solving the Newton step, every single step is going to generate a direction which is a descent direction. And so convergence of the methods, at least theoretically, is guaranteed. What you can lose is you'll lose things like quadratic terminal convergence and things like that. Now, if you're solving gigantic problems, you may not be interested in quadratic terminal convergence. You're interested in just solving it even to modest accuracy, but in some reason, you know, in the amount of time, for example, less than a human lifetime. I mean, that's your. But again, this is your problem for solving such big problems. This is your fault, I should say. Okay. So this is sort of the idea. Now, here are some examples. One is to simply replace the Hessian with a diagonal. Or another one is a band of this. and use that as the Newton step. Because if that's diagonal or banded, this can be solved incredibly efficiently. So that's one method. Another method, and I think we even explored these in 364A a bit, or maybe you did a homework problem on this or something. I can't remember. If you didn't, you should have. So you did? Okay. Another one is to factor. This is called the Szymanski method. Is you factor the Hessian every k iterations, and then use that for a while. And of course, that requires a method, a factor solve method. Now, in a factor solve method, oh, that just reminds me, I have to say something. In a factor solve method, if it's dense or in some dense factor solve methods, there's a big difference between the factor and the solve. The factor typically goes like n cubed, and the solve goes like n squared. Right? So what that says is you get weird things you can say. You can say things like this. I need to solve ax equals b. And you say, no, actually, I need to solve ax equals b, ay equals, ax2 equals b2, ax3. You want to solve it multiple times with multiple right-hand sides. In a dense factor solve method, it's the same cost. Because the expensive part was the factorization. Once you've factorized, you can solve, you've put an investment in, and you can now solve multiple versions of that problem very cheaply. That's the key behind this. Okay? Iterative methods, nothing like that, none. Want to hear the cost of solving ax equals b by an iterative method, if that's like c, then the cost of solving ax equals b and ax tilde equals b tilde, along with the other one, 2c. There's no speed up. You simply call the solver again. Everybody see what I'm saying? So some things that you probably just got used to thinking about. For example, if you factor, back solves are essentially free because they're an order less. Now don't transfer to these iterative things. Okay. So this is the Szymanski method. It also works quite well. Okay. Truncated Newton method is very, very simple. It does this. You're going to run either CG or PCG, and you're going to terminate early. And in fact, it's very important to understand the key is not to terminate early. The key actually is to terminate way early. That's kind of the hope here. That's if you want to get stunning results, it's going to have to be something like that. Now these also have lots of other names. They're called Newton iterative methods. It's also called limited memory Newton. It's also called limited memory BFGS. You end up with exactly the same. You have to go through all this horrible equations. Everyone has their different notation system. But in the end, you find out it's sort of the same method. So these methods have lots of names. Okay. Now, in a situation like that, the cost is not the cost. The cost per iteration is completely irrelevant. So the cost is measured by the number of CG. Actually, it's the number of calls you make to the multiply by the Hessian. That's actually that's the exact cost. Is that? That's the number of CG steps. And to make these things work well, you're going to need to tune the CG stopping criterion. You want to use just enough steps to get a good enough search direction. If you use too many CG steps, then you're going to get a nicer search direction, but it's going to take you longer to get there. If you use way too many CG steps, you're going to basically be doing Newton's method now. That's great because now, whatever it is, 12 steps, it's all over. But each of those steps is going to involve 4,000 CG iterations or something. At the other extreme, if you have too few steps, you're basically doing gradient. It's going to jam, and it's going to take a long time. Okay. Now, it's, of course, less reliable than Newton's method, which is essentially completely reliable. But again, with good tuning, good preconditioner, a fast Hessian multiply, and you need some luck on your problem, you can handle very large problems. I should say that I should say something else about these methods. Whereas one can write a general purpose convex optimization solver, and you've been using multiple ones. You've been using SDP-T3, Sedumi, all these things. If you think about it, that's really very impressive. I mean, that basically, they don't know what problem is going to be thrown at them. They can be scaled horribly. I mean, if you make it too horrible, it's not going to work. But they can be scaled horribly, all sorts of weird things. You can have weird, sick, flat, feasible sets, and all sorts of weird stuff people throw at these things every day. and they do a pretty good job. They're general purpose. Okay, so, but when you get into these huge systems, it's much more ad hoc, and ad hoc means literally, it means everything is built, for this. Although people have tried to come up with sort of general purpose iterative methods, and they're getting close with some things, I think, in some cases. But generally speaking, you're going to need to tune stuff. You're going to need to, it has to be for a particular problem. You have to say, I'm interested in total variation denoising, or I'm interested in this PET estimation problem, in medical imaging or so. It has to be a specific problem. I'm interested in this aircraft flow scheduling problem. Okay, so now the good news is this. Once you fix to a particular, it's, by the way, not a particular instance of the problem, but the problem class. Once you fix to one of those things, I am not aware of any case where these methods cannot be made to work. Obviously, that's not a general statement. I can't back that up by anything. But every time I've ever looked at any problem, as long as you say it's a specific thing, like it's a network flow problem, it's a circuit, it's a this problem, it's a gate sizing problem, it's a problem in finance or machine learning, these work always. They don't work in 15 minutes. They work in, takes a while, right? Maybe not a while. So that's kind of the good news of these methods. And it's kind of the answer to this. Maybe once a day somebody comes up to me and whines, often by email actually, because they're not here, but they come up, they whine, they go, my problem, CVX, I can't solve it, blah, blah, blah. And okay, and you're like, it worked fine for 10,000 variables, it doesn't work for 100,000. And I'm like, well, it's first of all, it's MATLAB. It's made so you could rapidly prototype your problem. You need to solve 100,000 variables, you need to know how these things work and stuff like this. So this is the answer to people like that. And they're like, I don't want to write my own software, it's too hard and everything like that. I'm like, then don't solve problems with 100,000 variables. Just go away. Don't bother me or something. But the bottom line is you want to solve a problem with 10 million variables, 100 million, in a specific area, right? Like a specific little area, it's going to work, basically. So it's going to require some luck, and it's not going to happen in 15 minutes. Okay, so here's truncated Newton method. You'll do a backtracking line search on this. You could do a backtracking line search on F as well. The typical CG termination rule is going to stop when this is your Newton system residual here, divided by the gradient, which, by the way, is the right-hand side. So this is exactly the eta that we had before. There's no reason, this is an okay one. It's just, all of these things are kind of heuristic and stuff like that. So exactly what you use to stop maybe doesn't matter so much. And what you'll do is you'll have simple, with simple rules, then you'll iter out at some constant number, and you'll have this epsilon PCG that's constant. And so this might be like 0.1. That would be a reasonable number there. You wouldn't want to put 0.01, and you sure as hell would not want to put 1e minus 4. 1e minus 4 says you're basically calculating the Newton direction. And there's no need for that. Well, maybe to get the thing up and running and verify your code works and stuff like that. You might start with a small problem and make this 1e minus 4 just to make sure you're actually calculating the Newton step. And it should look then exactly like the Newton trace at that point. But you might want this to be 0.1. So a more sophisticated method would adapt the maximum number, or this thing as the algorithm proceeds, and the argument would go something like this. It would say that, look, early on, you don't need to solve the Newton. The whole point of Newton is that it changes coordinates correctly in the end game. So that if you're stuck in some sort of little canyon, instead of bouncing across canyon walls as you would in the gradient method, you're skewed towards a direct shot at the minimum. That is what Newton's method is. So you'd argue that actually Newton's method at first, in many cases you're wasting your time. So then you might have actually at first, this might be like this might start 0.1, and then it might kind of go smaller or something, and that might modulate depending on how close you are to the solution. There's a lot of lore on this, and you can find this in books and things like that, but a lot of it is just to play with it. So that's it. You would find some theory on this, and it's mildly interesting and things like that. I mean, this would you'd find something from the 70s or 80s or something like that, or in some book that would tell you if you did this, you'd guaranteed superlinear convergence. I guess my response to that is, we're not really trying to achieve superlinear convergence. We're trying to solve problems with 10 million variables.
Right.
Yeah.
Like the backtracking line search tend to take like a long time. Is there?
It shouldn't. Why would it take a long time?
Because essentially, I guess it just starts. It like has to do a lot of queries to get to like. I guess it depends
shouldn't.
on your criteria for.
It should not.
Should it?
Yeah. General rule of thumb is, you said beta equals a half, so your step size. Every time you query, your divide by equals 2. If you do 5 or 6 of those, that's too many. And the average number of line search steps you should be doing is like 3 or something, 2, no more. Often 1 point something. So I'm suspicious of that. I'm just telling you sort of what people experience. Yeah, that's not. And in any case, you have to evaluate F. You're going to evaluate it at every step here. Not every CG step, right? But every outer iteration, you're going to evaluate the gradient of F. And I haven't added that in to the cost here. So, yeah, that would come up. But yeah, you shouldn't be doing a lot of line search things, right? I mean, certainly, first of all, Newton's method, when you get into the end game, you're doing none. Right. If it's really Newton, you should be doing none. And that will translate over here. When you get down in the region of quadratic convergence with a method like this, you shouldn't be, even though you don't have exactly the Newton direction, which is aiming you right to the solution, it's a good enough direction that a full step should be taken. So it's actually kind of a bad sign if you're doing more than a couple of Newton steps. And if later in the algorithm, backtracking steps, if later in the algorithm you're doing lots of backtracking steps, this doesn't sound right. Oh, well. Is that a specific problem you're thinking of?
Yeah, I guess.
Okay, we'll talk about it later. Okay. Now you also have the question of CG initialization. One way is to initialize with delta x equals 0. It turns out in that case, the first step, if you go back and look at the CG thing, is actually it's very simple. You solve ax equals b. In the first step, you minimize over the line span through b. B, in this case, is minus the gradient. So the first, after one step of CG, to solve a Newton method, if you start from 0, what pops out is a very interesting thing. It's something, it's along the negative gradient direction. So if you take CG and you set n max equals 1, which means do only one step, then it turns out that the steps popped out by CG, in fact, are scaled versions of the negative gradient. So, and in fact, you can prove things like this. This is, there might even be a homework problem on that, in which case we'll assign it to you. Or maybe I forgot, or maybe but if there's not a homework problem, maybe there should be one, or something like that. You can prove the following, that when you run Newton's method, CG, to do an approximate Newton method, every step of CG takes your angle of your search direction closer to the Newton direction. Everybody see what I'm saying? So let me show you how that works. So here is, let's just make a quadratic. I mean, it doesn't really matter. Here you are. You don't know it's quadratic, let's say. And you are right here, okay? Now, the negative gradient direction says search in that direction, right? But the Newton direction says, no, I think actually that's a better step. That's Newton, right? If it's quadratic, it nails it in one step. And what you can show is this, that if you run CG, starting from 0, your first step will be in this direction, and every other step is going to actually close, they're going to simply move over here in angle towards the Newton thing. Okay? So, everybody see the idea here? So basically you bend you can even think of CG as sort of, modifying your step, taking into account more and more of the curvature, in fact. That's a good model for what it is. Okay. Now another option is this. You can actually use the previous one and do a warm start. Now, one problem with that is that if you start with 0, every step of CG, it will be a descent direction. And this might not be the case here. But you can give it an advantage if you're only going to do 10 steps. If that's what your tuning suggests, you can actually do really well by just using the previous one. And a simple scheme is something like this. If the previous step is a descent direction for the current point, use it, initialize this way, otherwise you initialize from 0. And these are just sort of schemes. So let's look at an example. It is L2 regularized logistic regression. So here's my problem. It's going to look like this. And if you want to know what this is I am fitting the coefficients in a logistic model right here. And there's L1 regularization over here. So, and what that means is you have a logistic model, you have a binary Boolean outcome, and I have a vector of features. And I have a giant pile of data that says, here are the features, and here's the outcome, like plus or minus 1. You know, like the patient died or didn't. And I give you 1,000. Or, you know, the stock price went up or it went down. And I give you, let's say, oh, to make it interesting, 1,000,000 features. Okay? So, and I might give you as few as 1,000 samples. Now, obviously, that's horrendously overfit. You're overfit by 1,000 to 1. If I give you 1,000 samples, 1,000 patient records, and 1,000,000 features. But what the hey, wait a minute here. Sorry. I'm going to have to go back and cut out that whole discussion. I thought that was L1. So, all right. We'll just rewind and skip all that. Sorry. We're just going to do L2 regularized. Actually, you can solve L1 if you can do this one, you can do that one. So, all right, we'll just do L2 regularized. Sorry, pardon me. L1 regularized would allow you to do it with 1,000,000 features. It would run, and it would come back with 37 features. And it'd say, here are the 37 out of the 1,000,000 that look interesting. These are the ones that I can make a logistic model and predict these 1,000 medical outcomes well, or something like that. Okay. Sorry, this is not that. This is just an example. Okay. All right. So the Hessian gradient look like this. They start looking very familiar. It's A transpose dA plus 2 times lambda. Lambda is diagonal here. The gradient looks very similar. And none of the details matter. But the important point here is all you have to be able to do is multiply by the Hessian, multiply vector by the Hessian. When you do that, you have to do this. And the key is here, you don't even form this matrix. Because this thing, it's easy to make up cases where I can store A, but I can't store A transpose dA. Let alone can I even think about factorizing it. That's a joke. But this is a case where I can't even store it, let alone factorize it. But anyway, I make this fast. I multiply it this way. So I need two methods. I need a method. By the way, this often corresponds to a forward model method, and that's a reverse or adjoint call. So I have a forward model call and an adjoint call, and I'm going to make two. For each, I'm going to make a forward model call and an adjoint call per CG step. And we'll just make an example here with 10,000 features and 20,000 samples. So here we just made up a problem where these XIs have random sparsity pattern. They have around 10 non-zero entries. And then the non-zero entries are just chosen random. None of this matters. But you end up with about, I guess, 500,000 non-zeros in this. And we made this small enough that we could actually do the symbolic factorization just to know what we're talking here. And so the factorization gave us 30 million non-zeros in the Cholesky factor. By the way, that's something we can handle. But as you can see, this method will just be like just orders of magnitude different. Okay, so the method is Newton, which we'll look at in a minute. And then truncated Newton with various things. We're stopping. Basically, we're max iterating out because we're asking for 0.01% error. And here's the convergence versus iteration. So these are actually iterations. And the Newton and the 250 step CG are right on top of each other. So the whole problem takes like, well, I mean, it depends what your accuracy is, but it takes like 15 steps. This is what we expect from our friend Newton, right? This is exactly the kind of thing we expect. Now, by the way, the cost of a Newton step versus the cost of 250 CGs is like just orders of magnitude off. The Cholesky factor had 30 million non-zeros. Okay, the original problem has something like 100,000 non-zeros or something like that. So you're just way, way, way off by orders of magnitude. The time for these, you can see here that if you do only 50 CG steps, you start losing a little bit, but not much. Now the 10 is actually, this is very typical. What happens in the 10 is you're making excellent progress, and then down here, that's this one, you stall. The theory says that'll keep going down, but we don't have time to wait for it. So that's the idea. Now the right way to do this is actually to look at the convergence versus cumulative CG steps. Now you see a totally different thing. Oh, by the way, Newton step would be like, I don't know, probably over in my office over there. The first Newton step in terms of effort would probably be, I don't know, we'd have to check, but probably way, way, way a kilometer that way. Okay? Just to put these things into perspective. Now let's see here. What you can see is very, very cool. This guy that does 10 CG steps, which is hardly going to win at any prizes for like good approximation of the Newton step, is doing like amazingly well, and then it just jams. By the way, if you're happy with a gradient being 10 to the minus 5 or whatever, like this is ridiculous. Cumulative number of CG steps is 100, and so you're solving a problem that I don't know how long it would take with a direct method, but this one might be in the order of like 20, 30 minutes or something like that. You're now back to solving it in milliseconds. So you're just orders and orders of magnitude faster. So here are some times, so we can actually get the times. So let's see. So if you do 50 or 250, you're basically the same. So here's Newton method with n max. And it jams near this gradient 10 to the minus 6, but that often is just fine. So here the time is 1600 as opposed to the 1600 seconds. So it's not bad. It's half an hour, something like that, as opposed to 4 seconds. Okay. So these numbers are these are pretty good factors here. These are worth going after. These factors. So these are just much faster methods. That's to hit. You have this one that jams or something like that. But you're already way off. I mean, you're down in the sub minute range. If you just do diagonal PCG, here's the same picture. And I think now it's simple. Now there's absolutely no doubt what the best thing to do is, and it's right here. You just do diagonally preconditioned CG to do your Newton method. 10 steps. Now, that's ridiculous. If someone says, what are you doing? You say, I'm doing a crappy job on Newton's method. And you say, really? How's it crappy? And you go, I'm using an iterative method to calculate the search direction. You say, well, what's your iterative method? You say, I'm doing 10 steps of CG, and then I quit. Then whatever I have at that point, I pass it to the higher algorithm to do a line search. Then you say, oh, do you have some theory that says that works? And you go, oh yeah, if I were to do 100,000 steps in exact arithmetic, I would have computed the Newton step. So, I mean, no one can possibly justify why 10 steps is enough here. I mean, you just can't do it. So that's it. But these things work now unbelievably well. And now that means you can scale. That means you can do a problem with 100 million variables like no problem. So here are the numbers for this, and they're kind of silly. It takes 1600 and it goes down to 3 seconds. Or it would be 5 seconds as opposed to like 45 minutes or whatever that is. So these are real factors here. Oh, and by the way, if you make the problem a bit bigger, this goes up much faster than this. Will just go up linearly. So you'll just if you were to make it 10 times bigger, you could solve a problem, and this would be a minute, and that would probably scale much worse than linearly. So, okay. I mean, you can use this for many things. You can use it for barrier and primal dual methods. And I think what we're going to do is quit here and sort of finish up this lecture next time. So we'll quit here.